Hey everybody, my name is Elior. I'm a data scientist at Data Science Group, and I'm going to be talking about Node2vec, which is an algorithm for embedding or creating dense representations for nodes and edges in any given graph. It's a 1-and-something-year-old algorithm. It came out in 2016 out of Stanford from Grover and Leskovec. And the agenda is going to be, we're going to start with what actually Node2vec tries to do. Then we're going to go over a little bit about how it does it, and that's actually the most important part. And we're going to finish with a showcase, which is coupled with a Python notebook, which you could all reproduce the results at home with a pip installable library that implemented the Node2vec algorithm. So let's start. So let's take, for example, a very simple graph, right? This would be the example graph. The node colors have no meaning whatsoever, but I want you to think about the edges as smaller the edge is, the higher the weight, right? So we as humans, when we see a graph like that, it's like very clear to us a lot of information about the graph. We can immediately see by the closeness of the edges that there's two kind of groups here, and we can also understand that node B to node A, which is gate to the outside world, has the same relationship that node 2 has to node 1. Now this is information that for us comes very natural when we look at graphs or when we think about graphs. But when we want to use graph data in downstream tasks, in our models, or any other things that we want to build upon it, we have to find a way to take that information and pass it on to our models. Because if we don't do so, if we will just use, like any kind of one-hot representation for nodes or what else, we put the burden of learning these relationships on the model itself. So we want to make our model's tasks easier by giving this information. So what Node2vec tries to achieve is to embed that information into some kind of a space that will encapsulate all that information. So this is what Node2vec tries to do. It tries to take the nodes that are actually close together in the graph, that are strongly connected, and create closeness in the embedded space. And it will also try to make the relationship or the vector that points from vector A to vector B the same or very similar to the vector that points from node 1 to node 2. So this is what Node2vec tries to achieve. So how does it do that? Before I go to the next slide, I think it's best to explain Node2vec through Word2vec, okay? Because Node2vec actually builds upon the successful foundations of Word2vec. Word2vec came out 2 years before that and actually changed a lot of the NLP world and had a lot of success in various fields. So it's only natural that other algorithms will build upon it. So if we will think about how Word2vec works in like a modular way, we're not going to go very deep into that because it's out of the scope of this talk. But in a modular way, Word2vec takes as an input an array of sentences. And what it does, it generates from that array of sentences some kind of input data to what is called the skipgram model. This data gets fed to the skipgram model. And from that skipgram model, we then draw the embeddings. So you might ask, like, OK, Word2vec is nice, but what does that has to do with graphs and nodes and Node2vec? So we have a problem that is already solved. We know how to take sentences and embed them. So if we would find a magical way to take a graph and reduce it into sentences, we will actually solve our problems. So now we started with embedding graphs. Now our problem is like a little bit different. We need to take any graph and turn it into an array of sentences. So how do we do that? That's kind of weird too. So let's think about sentence. What is a sentence? A sentence is like a sequence of tokens, and it has a specific direction, right? If we would to read this sentence, we know where to start. Okay, abstraction is often one floor above you, a nice sentence. So we understand the structure of this. We know the first word is abstraction, and the next word is, and so on. So in some kind of way, this is a specific kind of graph, right? Where each word is a node, and the edges are just the characteristics of this sequence. Okay, so now it started to make a little bit of sense. Now, all we need to do is to reduce the graph into an array of this specific type of graphs. So this is the problem that Node2vec secret sauce really solves. It takes a graph, any graph, and it has its intelligent way of creating this array of this specific type of graphs. So how do we do that? Given that we are talking about any graph, it could be directed, undirected, it could be cyclic, it could be weighted, unweighted, it can even be unconnected, like separate graphs. And this is done by what is called random walks, which is quite a bad name for that because it's not really random. We control the randomness of these walks. But the idea is that we're going to use what is called a sampling strategy, which we'll talk about in the next slide, so don't worry about that. We're going to use this sampling strategy to generate random walks from every node in the graph. And those random walks are actually look like this one, because when we start from a node and we start to traverse it to another nodes, we can just collect this kind in any kind of walk. So the first walk might look like this one, and the second walk would look a little bit different. And then we would gather all of these walks, and we basically just generated lots of sentences out of our graph. Okay, so let's talk about random walks and how do they work and how we control them, because this part is actually really important, because we control the walks, we actually control the information we want Node2vec to gather from our graph. So the hyperparameters are not so many. First one is the output dimension, right? We're gonna embed nodes and edges. First have to decide the output dimensions of the embeddings. The next thing is the number of walks. Number of walks actually says how many times I'm gonna start a random walk from each node in the graph. The third one is the walk length, right? I'm going to start walking from each node, but how long am I going to walk? So these are like the three basic ones. And then comes like the secret sauce, you might say, of Node2vec. So okay, before we actually talk about the hyperparameters, when we will think about the probability to traverse from one node to the others, the most naive way to do it by normalizing the weights, right? If it's like it has a stronger connection, it has a higher weight, it will get a higher probability to travel from one node to another. But that doesn't give us enough flexibility, because sometimes the weights are given. So what Node2vec offers is two additional parameters, which are controlling the search bias. The search bias is the characters represented by the character alpha actually gets multiplied by the weights, and after we multiply the search bias by the weights, we normalize them, and then we get the probabilities of transitioning between one node to another. And through that, we control the way we travel. So let's explain these two parameters. First one is the P parameter, the return hyperparameter. And consider this small sample of a graph when we just started a walk and we transitioned from T to V, right? So we are in V and we came from T. The P value, which is the return hyperparameter, controls the likelihood that we're going to go back from V to T. If we set a low P parameter, we increase the probability to return back, and actually we just say, I want to emphasize the connections on the local level. See, like the graph could be huge. I want to emphasize the local structure of the graph. So that's the P return hyperparameter. The Q actually controls what you might think about if you're going to be traveling on the graph in a BFS way or a DFS way. So imagine that we set a very high Q value. We will actually lower the probability to go deeper. We will favor a BFS-like search than a DFS kind search. And we will set it to a very low value, then we will increase the importance of global structure in the graph and encourage exploration throughout the entire graph. So this is like really important to understand this jointly with what the script gram model of Word2vec really embeds, which I do have a link on the last slide that I do encourage anybody that doesn't understand the script gram model to read about, because it's very important to understand what kind of information the skipgram embeds in order to use Node2vec to its fullest. So now we know how to create the sentences. We basically know all the process that Node2vec does, and let's see a use case of how we control the graph and its structure to eventually decide what information we want to embed. So the showcase is going to be on the FIFA 17 data. So pardon my geekiness, but I'm a FIFA player. So this is what I chose. It's actually available on Kaggle. It's a bunch of tables representing team structures from various clubs that are playable in FIFA. So what does like football team has to do with graphs? Any team is represented by a formation, right? Any team has like a striker, a left winger, a central midfielder, stuff like that. And they are connected in some kind of way. Now there's a dozen of different formations connected in different ways. There are dozens of different players and teams, and each one is connected in a different way. So in order to do this showcase, which as I said, you can later find on the notebook, first of all, let's try to think what we are trying to achieve. So we are going to have three types of nodes. We're going to have player nodes, which are like Cristiano Ronaldo, Messi, all those type of guys. We're going to have team nodes, which represent the team itself, like Madrid, Barcelona, etc. And the last type of node is going to be a generic position node, like a central midfielder, central back, a goalkeeper, and so on. And the idea is what we are trying to achieve is something that to us humans comes very naturally, right? If I ask you like what is most similar to a goalkeeper, you can name goalkeepers from different teams. That's what we want to embed in the space. If I will ask you who is the most similar player to Paulo Dybala, I would expect you to say players that play like around him and can exchange him in the field. So this is the kind of information we're going to try to embed. So how are we going to do that? How are we going to construct our graph? First, we're going to take each team and create specific player nodes given that team. So like this could be, I don't know, Cristiano Ronaldo, this could be the one who plays beside him, and all of them are going to be connected to the team node. I didn't draw that because it would be very cluttered and messy. And we're going to do that to any team in our data. I did it specifically on 7 clubs. So any team is going to be connected between itself to according to the formation, and we're going to add we're going to be adding the generic nodes. So these generic nodes are also connected, but I didn't include the edges, so I will be able to explain what's going on. And the last type of connection we're going to be making is connecting between the actual teams and the generic positions. So the central midfielder, since he's connected to his central back CM2 and CB2, he is also going to be connected to their generic positions. And you will see in a minute why that is important to embed the information we talked about. And similarly to the goalkeeper. So now we're going to start the random walks, and let's consider how many ways there are to get from CM2 into GK2 on the right side team. So one way would be CM2 through the generic position to the goalkeeper. A second way to do that will be through the literal central back. So what have we done here? When we look at these two sentences, right, we can see that the generic position CB, which is in yellow, actually gets the same context as CB2. And by creating these kinds of walks, we are basically teaching the algorithm or giving it the ability to learn that the central back generic position is similar to CB2. Why? Because they appear in similar context. And that's That's part of the thing. And if we will do the same to the second team, we will actually get a connection between the central backs of the other teams, right? We can see that if CB1 is similar to CB and CB is similar to CB2, we will get the result that CB1 and CB2 are really like something like of the same. And also another thing that we gain here, since if we will look at the first sentence and the third one, we will get that the relationship between the central midfielder, or CM2, to GK2 is the same relationship between CM1 and GK1. And okay, that's all hand waving and stuff, but let's see if this actually works. So this is taken from the notebook, some kind of results of querying the space that was outputted by the algorithm. And the first thing I did was like, I'm taking a generic position, a right winger position, and I'm looking for the most similar nodes in the graph to that generic position. And it must be gibberish to most of you, but these are actually right wingers, right? So anyone who does know can back me up here. So these are all indeed right wingers. And the next thing we wanted to do is, if I'm going to query a specific player, I would expect to see his teammates around him. So the next thing we do, we are querying Paulo Dybala, which is a Juventus player, and we can see also his team node here and all of the players that play with him. Okay, on the same team. We're only seeing 10 because that's the default setting of the top and most similar. The last thing, which actually is not on the notebook, I just added it today, so it's not on the notebook, but you can replicate it yourself, is the king, queen, woman analogy from Word2vec. So what I'm taking here, I'm taking a goalkeeper from one team, and I'm subtracting a central back from his team, and I'm adding a central back from another team. And what I get is actually the goalkeeper from the other team. And that's quite amazing at least for me to watch. Buffon doesn't actually play for Juventus anymore, but this is 2017 data. So that's about like querying about relationships in the space. The last thing I did is I actually used tsnit to reduce to 2 dimensions, and we can actually see that we kind of see the formations of the team here, and we can see the clusters of the different teams, which are nicely separated. And this like wasn't really handpicked. It really does so like that. We can see that the information that we wanted to embed really got into the space. We found local relationship with similarity between players and between players to the generic nodes. We got long distance relationship, like between a goalkeeper and his striker to a striker and another team to his goalkeeper, which is a similar relationship. And this kind of information is the exact information that we already have we accumulate, as we get to know graphical structures without any need of special training. But the challenge to pass this information on into any downstream models that we are going to be trained is actually answerable by Node2vec. Before we go into the questions, this is our useful links. So the first one is the original article, which is very friendly to read, so I recommend it. It's not like most articles that try to keep you away. The second one is a Python 3 library, which I have written and implements the Node2vec algorithm. You can just install by pip install. The third one and the fourth one are actually a Medium post and the notebook, which does all the magic we just talked about the FIFA data. And the last one, which is really important, out of the scope of Node2vec, it's a great post that explains the rationale and the mechanics of the skipgram model, which is behind Word2vec. And as far as I can tell, it's very critical to understand it. So you could use Node2vec and even Word2vec to its fullest. And that's it. Any questions?
What is the incentive behind it? What are the uses of vectorizing the nodes?
Okay, the most use cases that I can think of is when you want to use data that is represented by graphs in downstream tasks. You can think about, let's say, what they are doing in the paper itself. They're using models on top of this to predict links. Think about Facebook, okay? Facebook has many nodes as people and links as friends, and they might want to suggest you, like, who is the most probable node that would want it to be a friend. So this is one kind of use case. Another use case that I actually applied this to was hierarchy. You know, there's actually a method to embed hierarchy, which is called which is like explicit method to do that, which is called the Poincaré embeddings, which came out of Facebook like last year. But from what I could tell and from what I have tested, it actually works better if you just represent the hierarchy as a graph and you just embed it, and it worked better as far as I can tell. Thank you very much.